Okay, I'm going to talk about section 6.1 today, area between two curves. We're going to start off with some generic examples so we can kind of see how we're going to do this when we're actually given functions to find these areas. The ones over here are actually things that we've been doing since way back in the first chapter, area between a curve and the x-axis. So I just want to refresh our memories on this because we're going to use these ideas over here for when we do area between curves. Okay, so this is kind of the standard thing. How do I do the area under a curve, or between a curve and the x-axis, I should say more specifically from A to B? Well, that's simple. We're just integrating from A to B, f of x dx. And the one thing I just want to remind you that is this notation has special meaning for area. This is a notation that means the rectangle. So if you think about it, f of x would be the height of our rectangle. The width of any one of our rectangles will be dx, dx being an infinitesimally small change in x. In other words, infinitesimal being sort of the smallest value you can get, not zero. There's not a fixed number like that, but we just think of something as sort of approaching zero. So we take the height of our rectangle times the width, making it so there's an infinite number of these rectangles, and then we sum them all from A to B. So that's what that means. Okay, so if I want the area between f and the x-axis from A to B, if the curve's all above, no problem, we're just integrating from A to B, f of x dx. Okay, over here, we all know that if I just integrate this straight across from A to B, I'm going to get a negative value, correct? So since I'm going to get a negative value here, and I want area being the positive area, what I need to do with this one is I need to negate it so that it turns back to positive. So of course, the integral from A to B of f of x being below the axis will give us a negative. So then we have negative, that will bring us back to positive. And finally, this one where it starts above and then goes below, I've got to break this into two separate parts. So I would integrate from A to B, f of x dx. So since that's above the axis, this is going to give us the area. But then from B to C, it drops below, so I'm going to subtract it. Since this is negative, I'm subtracting that negative number and it will be adding it. So I'm going from B to C, and that's f of x dx. And like I said, these are things we've been working on since way back in the first chapter, so we should be pretty comfortable with that. Okay, so now let's talk about area between the curves. The first one I think most of you will get. So if you think about it, if I want this area, I'm going to go from A to B, f of x dx, okay? And then what I'm going to do, right, because that's just going to give me all of this, right? That's going to give me all under f. And then what I want to do is subtract the area under g. So I'm going to subtract the area from A to B of g of x dx. Now what we end up doing is, it's actually fine if you do it as two separate integrals, but realize we can put both these in the same integral. So if I see something like this and I want area between f and g, I would just do one integral, A to B, f of x minus g of x dx. And that, you know, especially if I'm doing this without a calculator, that's going to save me some time, because so I can do some simplifying in here. It's going to make this a little bit easier. Okay, so let's think about this one. So this is what we're going to use here. Okay, so what about this one? We'll realize that I can think of this as two areas. So I have this area above, right? Well, that's just going to be A to B, and then f of x dx. So that's going to give me that area above. And then below, since g is below the axis, what I can do is, to get this area, right, I'm going to add the area below, which will be the negative of this thing, A to B, g of x dx, okay? So I'm adding the area above, and I'm adding the area below. The area below would be negative. Now what I realize is, since I'm adding that negative, right, because this is this area below, once again, all I'm really doing, because adding a negative is the same as subtracting, is I'm taking the function above and I'm subtracting the function below. It does not matter, like it does over here, that this function's below, because that will take care of that. So the moral of the story is, I'm going to put this in the box, moral of the story is, let's get rid of this. So adding the area above, adding the area below, which we put a negative because that's going to return a negative value. This one is also the function above minus the function below. And so the reality is when we do area between curves, as long as one curve stays above the other, it's always function above minus function below. We don't have to think about, we have to think about what this is, which would be in terms of the x-axis. So for instance here, this one, does not matter where the x-axis is. The x-axis could be up here, it could be below, it can cross through like we have here. It's always just going to be the integral from f of x minus g of x dx, the function above minus the function below, from a to b. It does not matter where these functions are in reference to the x-axis. So area between functions is quite easy. Function above minus function below. And then you integrate it. By the way, you could have thought of this like that, because if you think about it, this is like the 0, right? The x-axis is a 0 function. So this would be 0 minus f of x. And then this, I'm just showing that it matches up. This would be f of x minus the 0 function. Okay. And this one, obviously, we have to do two separate regions. All right. So the moral of the story is, whenever we do area between functions, it's always the integral of the function above minus the function below. All right, let's do some examples today. Okay, this is our first example we're going to do. We're actually going to do 3 examples. The first 2, we're going to take a closed calculator approach, and then the third we'll take an open calculator approach. So with a closed calculator, it's good to get a sketch of the graph. What I'll tell you about this is it doesn't have to be really all that accurate. It just has to be accurate enough that I can set up my intervals. So we want to find the area between the following graphs. So we have this line, this upside down parabola, this vertical line, and this vertical line. Okay. So let's go ahead and start off. So like I said, this one is pretty basic. Let's start with y equals x plus 3. Keep in mind, we're only talking from the vertical line x equals 1 to 3. So typically when they give you these vertical lines, they're essentially giving us what the integral is. So this would be 1 to 3. I pretty much know that already. So x plus 3, we know that has a y-intercept of 3, but we're more interested where it starts off at 1. So if I plug 1 in that's at 4. Okay, like I said, I'm not worried too much about this. I just want sort of a rough graph here. So 1, comma 4, and then when I plug 3 into this, I get 6. So that would be 3, 6. So this is our first equation, y equals x plus 3, okay? And then we have our second equation, which is the upside down parabola. We know that starts at 0, 0, but once again, I'm interested in what it is at 1. So at 1, it's at negative 1, and then at 3, it's at negative 9. So you'll see I already include that. So it looks something like this. And that's really all I need. I don't need any more detail than that. I don't need x-intercepts or anything like that. So keep in mind what we're talking about is the area between these two curves. Okay, and like I said, we're doing this one closed calculator. So we have to calculate it by hand. Okay, so as I talked about earlier, this is always pretty much the same. It's function above minus function below. Don't worry about where the x-axis is. In this context, area between curves, it simply does not matter. This one's y equals negative x squared. So we're doing x plus 3 minus, and the function below, which is negative x squared, and then dx. Okay? Now, we do have to calculate this, so my advice to you is simplify this. So this simplifies into a very simple trinomial. So negative, negative, that'll be x squared plus x plus 3 dx. Now we have to take the antiderivative. So this would be 1/3 x to the third plus 1/2 x squared plus 3x. Now, as always, take the derivative of that, make sure it matches up. So looks like we're good. And then we're integrating from 1 to 3. I will tell you with these, we got to do some arithmetic. There's really no way around it. So 3 goes into here, right? And I get 3 to the third power. That's 27. But then we're multiplying by 1/3, so that's 27 divided by 3, that's 9. Okay? 3 goes in here. 3 squared is 9. 9 times 1/2, so that's 9 halves. Okay? And then 3 goes in here. That's plus 9 as well. Okay. So our next thing is we are subtracting 1 plug in. Do that right. 3 goes in. 3 through power is 27. 27. Yeah, looks good. Okay. Minus 1 goes in. So that's easy because all of these we're just going to be left with the coefficients. Make sure you have parentheses. We're going to subtract all of these. So this will be 1/3 plus 1/2 plus 3. Okay. Now what we want to do is combine what's happening here. So realize that, and if you want to do this with your eraser, I'm distributing this negative. So this will be minus 1/3 minus 1/2 minus 3. Okay, whatever works best for you. So 9 plus 9 is 18, minus 3 is 15, so I have 15. And then 9/2 minus 1/2 will give me 8/2, which is 4, okay? And then minus 1/3. Okay, so 15 plus 4 is 19. 19 minus 1/3. So I've got to multiply 19 by 3. So 19 times 3 is 57. 57 over 3 minus 1/3 is equal to 56 over 3. And we're just going to leave it like that. Now, if you would like to check, you can always do that because you can use Math 9 and check with your calculator. But that's our answer. So when we do this closed calculator, you know, we've got to do the fundamental theorem of calculus, the antiderivative, we've got to show all that stuff. Okay, like I said, we're going to do 3 examples total. So we'll do one more closed calculator, and then on the third, we'll do open calculator. Okay, example 2. Find the area of the region bounded by the graphs of these functions, f of x and g of x. This is a little bit different. Before, I was given actual vertical lines. This one I'm not. So in this case, I need to find what the intersection is so I can graph these. Once again, without a calculator, you know, typically these things are going to be things we can figure out. This is obviously a parabola that opens up, and this is a parabola that opens down, so we're expecting 2 intersection points here. So we need to find those intersection points first. So I'm going to set them equal. Okay. Let's see. Let's move everything over here. So this will be, let's see, 4x squared, and then minus 4 equals 0. They're kind to us here because we don't have a trinomial. This will be easy to factor. So notice I can factor out a 4. That gives me x squared minus 1 equals 0. And then this factors the difference of 2 squares. So that's x plus 1, x minus 1 equals 0. So I get x equals -1, and I get x equals 1. Now, just to give me some reference of where these fall on the graph, I'm going to go ahead and get the points, so when I graph them, I have some details here. I will tell you that, once again, these graphs just have to be good enough for us to set up our intervals. From there, it does not matter a whole lot. But anyways, let's plug -1 into that. So realize that's going to be positive 1. So that gives me 3 minus 1, that's 2. So I get -1 comma 2. And oh, by the way, the same thing happens with 1. If I plug that in, I get 2. So this is 1 comma 2. So really, if I just start with those points, I'm going to do a little graph right here. So I've got -1, 1, and then 2, 2. I've got a parabola that opens up and goes through those points. I do not care at all about what its y-intercept is or where it crosses the x-axis. None of that matters for this question. Because keep in mind, when we do area between functions, it does not matter where it is in reference to the x-axis. Okay, and then this one is a parabola that opens upside down. Once again, it crosses these points. Once again, I do not care about anything other than what those intersections are. So this is my g function above and my f function below. So we're talking about the area between these two curves. So this time, the intersection points define the interval. So let's go ahead and do that. So we're integrating from -1 to 1. We're doing the function g. So 3 minus x squared minus the function f, which is below. Make sure you put that in parentheses. Okay. Now we do want to simplify this. So -1 to the first, or excuse me, -1, and then the limit on the top is 1. So 3 minus x squared minus 3x squared plus 1 dx. So that's going to give us, let's simplify this, -1. I think it is in our best interest to simplify this as much as we can. So let's see, that's going to give me -4x squared, and then plus 4 dx. Okay, so now we have a nice clean integral here to integrate. So let's go ahead and do that. So raise that a power, that'll be x to the third. So this will be -4/3. So when that comes down, the 3's cancel, bringing back to -4, plus 4x. And we're integrating that from -1 to 1. Okay, so let's plug the 1 in first. So we're gonna just have the coefficients here. So this will be -4/3 plus 1, plus 4, minus, now be careful with this, we are plugging -1. If we plug -1 into the odd power, it stays negative. So this is actually going to be negative coming out of here, times that negative will give us a positive 4/3. And then -1 going into this will be -4. Okay, so let's do some simplifying here. So we get -4/3 minus 4/3, just moving that next to there. And then we have plus 4 plus 4, so that's 8. So what I get here is 8 minus 8/3. So this we want to call 24/3, right? That's still 8 minus 8/3. And so what we get is 16/3. And that is the area between the curve. Once again, if you want to check that, you can go ahead and use Math 9 to check. Okay, so that is example 2. We're going to do one more example, and this one we're going to use our calculator, so go ahead and get your calculator out. I'm going to walk you through how to do this. Really, there's nothing new here. We know how to use all these features from before. The reality is when we're doing these open calculator, it's a lot nicer because we don't have to do the antiderivative and all that arithmetic. Okay, example 3, find the area of the region bounded by the graphs of the function f of x, which I have up here, x to the third plus 4x squared minus x minus 10, and g of x, which is equal to negative e to the x minus 5. Now the first thing you want to do, once again, open calculator, is we want to put these in our calculator. I want to remind you, when you actually submit these for work, make sure you're using the notation they give you, not the calculator notation. We don't want y sub 1s and y sub 2s, but I will be including that so you know what to enter in your calculator. So let's just go ahead and enter this as y sub 1. Okay, let's enter this as y sub 2. All right. Now, when we graph it, and by the way, if anytime you want to pause this video so you have time to enter it in your calculator, go ahead. I already have it ready to go to be more efficient with my time. So anyways, put that as y sub 1, put that as y sub 2. If you started with the Zoom standard, the -10 to 10, -10 to 10, you will actually see the region. And this is not region, this is regions, which we'll see here in a second. However, to get you a window that gives you a really sort of focused look, if you go with x going from negative to 6 to 4, and then y going from negative 12 to 3, you get a more sort of focused look at these graphs. So if you go ahead and set it like that, and what you should see is a function, might as well do colors here. We really don't care where it is in reference to the x-axis, just broad strokes here. A very sort of rough graph is perfectly fine here. Okay, so anyways, we get something that looks like this. That is our f function, which we have in our calculator as y sub 1. And then the g function, which should look something like this. Okay, so understand there's actually two regions we're interested in. We're interested in this region, okay, and we're interested in this region. Now, there's a trick you can do here, but I don't want to get into that. So just understand that we actually have to do this as two separate intervals. Area above, or excuse me, the area here, we'll do g minus f, and then, excuse me, other way around, sorry. You have to watch. So this is f here, right? The blue function is f, and then this is g. So for our first region here, we're going to do f minus g, and then over on this side, they trade places. So now the g function is on top, so that'll be g minus f. So I'm going to do this as two separate intervals. Now, typically when you're doing these as open calculator, these are not going to be nice values. So like we've done in the past, we are going to have to find the intersections, and we're going to have to store them. So before I do that, let's just go ahead and mark these. I'm going to store these as A. This intersection I'm going to store as B. And this intersection here I'm going to store as C. So we're going to figure out what those are. Okay. So let me walk you through this again if you forget. So if you go to your graph, we're going to do second calc. And we want intersect. So intersect. As long as these are the only two curves you have as y sub 1, y sub 2, as long as you don't have something else, you can just hit enter, first curve, enter, second curve. And then the guess, just sort of move it close, or you can plug in, I don't know, looks about 1, 2, 3, about -3, okay? And it's actually a little to the left of that. So now I'm gonna go to the home screen, so it's about -3.9322. So if you remember, we go to the home screen, and I'm actually going to write this on my paper so I can use this throughout. So if you go second quit, and temporarily it will store whatever intersection we did as x. So I'm going to do x, that store button, stow, which is right above beyond, and I'm going to hit alpha A, and now I have that in my calculator as -3.9322. So I have that in my calculator. Now I'm going to repeat that process with B and C, okay? And once again, if you need to pause to do this, go ahead, but I already have this in my calculator, so I want to save some time here. So once again, go second calc, intersect, first curve, hit enter, second curve, hit enter, and then this time move your cursor kind of close to here, or choose something like -1 or something in that ballpark. And we're going to get those two other values here. Once again, go to your home screen, X store alpha B, and then for this one, X store alpha C. So the values you should get here are -1.1099 and 0.8506, and I have those stored. All right. Now, once we label those on our paper, we can use the A, B, and C. This is really good in a free response question because often you'll use these multiple times. So this way, if you store them as A, B, and C right down in your paper, then from then on in the problem, you can just write, keep writing A, B, and C. So let's go ahead and set this up. Don't use your calculator notation here when you set this thing up. We want to use the notation that they provide for us. So the first one, we're integrating from A to B. All right, I already have that written down, so I don't have to write it again. And it's f of x minus g of x. There's no need to use all this algebra here. F of x minus g of x is perfectly fine. Since we're just letting the calculator do the work, we don't need all that algebra there. And then we're adding that to the area from B to C. This time it's g of x minus f of x, and then dx, okay? That's our setup, that's all we have to show. From the rest of this, we're gonna use our calculator. Now, what I'm gonna write here, just keep in mind, this is for you, for your notes, but this will not go on your paper. So whatever setup you have, you're gonna do math 9, you're gonna go A to B, and then function f is y sub 1, so vars, y vars, function y1, minus vars, y vars, function y2, okay, dx, plus, and then B to C, and then we're reversing this. So g is our y sub 2, so y sub 2 minus y sub 1, and then dx. And once again, this does not go on your paper, that's just for your calculator. So let's go ahead and calculate that. Once again, if you have to pause this to do any of that, feel free. So math 9, alpha A, alpha B, vars y bars function y1 minus vars y bars function y2 dx. And then I'm going to add math 9. That is alpha b to alpha c. Vars y bars function y2 minus vars y bars function y1. And go ahead and hit enter. And what we get is 18.3091. And as always, make sure your final answers are accurate to 3 decimal places, truncated or rounded. Same with these. Make sure those are accurate to 3 decimal places. On your paper, you can go ahead and round them as long as you're storing these in your calculator to ensure you're accurate. So here's our answer. So once again, like we've seen in past sections, when we're doing the open calculator stuff, you really aren't doing any algebra like we do on the closed calculator. It's just about making sure you know how to operate your calculator, make sure you know how to store your values, etc. Okay, so that is area between curves. That's the end of that video.